everyone, my name is Logan and welcome back to the lecture hall. Today we're covering section 5.2, the definite integral. From our previous video we found that the limit as n approaches infinity for the sum from 1 to n of f of xi delta x is just equal to this, is equal to the limit as n approaches infinity of f of x1 times delta x plus f of x2 times delta x plus, all the way up to plus f of xn times delta x. Okay, cool. But now we get a definition of a definite integral. So what is a definite integral? If a function is defined on a to b, we divide the interval a to b into n subintervals of equal width, such that delta x is equal to b minus a divided by n. X naught is equal to a, x1 is, x1 is a plus delta x, and so on all the way up to xn is equal to b. And these are the endpoints of each subinterval. Then let x1 star, comma, all the way up to xn star be sample points in those intervals, such that xi star is in the subinterval. And this looks a little weird, but they're just points that we're pulling from the intervals. They can be any point in the interval. Then we get the definite integral of f from a to b is, well, this curly symbol, a to b, so a is on the bottom, so if this is your lower bound, this is your upper bound, of f of x dx is equal to, well, this. It is equal to the limit as n approaches infinity from 1 to n of f of x I star times delta x. And we're like, wait a second. This is how to solve our area under the curve from our last video, and then we get, well, hey, now we get something even nicer, where it's just this sweet little curly thing of f of x dx. And so what this does is this finds the area under the curve for our function. Alright, now that we know the definition of a definite integral, we have to go over some notation. So, this is our integral. This little curly s symbol, like a stretched out s, this is our integral. Our f of x is our integrand, and then our a and b are our limits of integration, where a is the lower limit and b is the upper limit. Okay? And then now we have this sum of f of xi times delta x, and this is our Riemann sum. And this is named after the mathematician Bernard Riemann. So there may be a question that states, oh, find the Riemann sum of the curve width for rectangles or whatever. So then what you would do is you would go from 1 to 4, because our n is our number of rectangles, and then you would just plug it into this formula, and that's our Riemann sum. Alright? Now, how does finding the areas work? Well, we know any area above the curve is positive, any area below the curve but above the x-axis is positive, any area above the curve but below the x-axis is negative, and so on. So, before, what we had to do last video is we had to break it up into these little rectangles, right? Okay, we break it up into these little rectangles, whether they're overestimations, underestimations, whatever they may be, and we would have to just add up the areas. But now, we get this integral from a to b of f of x, and basically it is equal to one area minus another area, which is equal to big F of b minus big F of a, where our f of x, our big F of x, or our capital F I should say, is the antiderivative of f of x. And what that'll do is that'll actually just give us all the area under the curves without having to add up these areas with little rectangles. Now that we know what a definite integral is, it begs the question, when can we actually evaluate a definite integral? And we actually have a theorem for this. It states, if f is continuous on a to b, or if f only has a finite number of jump discontinuities on a to b, then f is integrable on a to b, which implies the definite integral is the integral from a to b of f of x dx, and it exists. Okay, well that's kind of scary. You say, what? Finite number of jump discontinuities? Don't worry for this class. You don't need to know what that is. That's more dealing with the proof later when you build on the mathematics and analysis. So don't worry about this finite number of jump discontinuities. Just know function has to be continuous and then the integral will exist. We get another theorem. If f is integrable on a to b, then the integral of a from a to b of f of x dx is equal to this limit from as n approaches infinity from I 1 to n of f of x I times delta x. And, well, we know this from our previous video. Delta x is equal to b minus a divided by n, and then our xi is equal to a plus I times delta x. So these are our two theorems kind of saying, okay, our definite integral exists here, and when it exists, this is what it's equal to. Now we are on to some summation laws. We have the sum from I to n, or 1 to n, is equal to n times n plus 1 divided by 2. We have the sum from I equals 1 to n of I squared is equal to n times n plus 1 times n plus 2, all divided by 6. And then we have the sum from 1 to n, or yes, 1 to n of I cubed is equal to, well, the sum from 1 to I squared, it's n times n plus 1 divided by 2 squared. Okay, cool. Next, what do we have? The sum from 1 to n of c. And what is it saying? Well, it's just saying count up c n many times. Well, that's just going to be equal to n times c. Okay, now we have the sum from 1 to n of c times ai. Well, that's just equal to c times the sum of ai. So your ai can be whatever, and you just multiply c at the end, and then you get your answer. Okay, now the sum of ai plus bi is equal to the sum of ai plus the sum of bi. And then the same for the difference. The sum of ai minus bi is just equal to the sum of ai minus the sum of bi. Now we can go on to a little bit of a approximation, how we can make our Riemann sum better. What we can do is we have our Riemann sum, this is our integral, right? And it's saying this is approximately equal to, and why do I say approximately equal? Well, I don't have that limit there, so we can't say it's exactly equal. And we see this, well, f of x bar I. Well, and then times delta x. Well, our delta x stays the same, and it's equal to b minus a over n. But now our xi bar is equal to 1/2 of xi minus 1 plus xi. And what is that? Well, that is the midpoint in here, in between the interval xi minus 1, comma xi. And so that is the exact center point in that interval, and what that will actually do is give us a better approximation when we do our Riemann sums. So there might be questions like, find the right-hand Riemann sum of 3 rectangles, find the left-hand Riemann sum of 3 rectangles, and find the midpoint sum of 3 rectangles. And then you'll probably see that the midpoint will be the most accurate. It'll be in between the overestimation and the underestimation. We have some limit laws now, and this states that the integral from b to a of f of x dx is just equal to the negative of the integral from a to b of f of x, right? So what are we doing? We're taking our bounds and swapping them. And what that is going to do is swap the sign of the answer. So it just becomes negative. And then let's say if a equals b, then our delta x is equal to 0. So what does that imply? Well, that implies that our integral is just from a to a. But what is the answer? Well, think about this. If our delta x is 0, well, then it makes sense that this is equal to 0, right? Because you're not getting any area because there's no width. So just notice if you see, oh, the integral from 2 pi to 2 pi of some nasty looking function with cotangents and stuff, well, it's just from a to a, so it'll equal 0. And now we are on to some other ones, and these are consistent with our summation laws. We have the integral from a to b of c dx. What is c? C is just a constant. For our purposes, it's just going to be a constant in r, but it also could be a constant in the complex numbers as well. But for this class, it's always going to be an r. And this is equal to c times b minus a. Okay? And And then the addition law, the integral from f of x plus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Okay, why is this nice? Well, maybe we have a function and it's just kind of gross looking. You can split it up. Same thing with our constant times a function. We can bring it out. So we have the integral from a to b of c times f of x dx. Well, that's just equal to c times the integral from a to b of f of x dx. Okay, and then we have the difference law. We have the integral from a to b of f of x minus g of x dx is equal to the integral from a to b f of x dx minus the integral from a to b of g of x dx. Some more integral properties are, if we have an interval from a to b and we have c in that interval a to b, then the integral from a to b of f of x dx is actually equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And this should kind of make sense, right? Because you have some curve, right? And then you cut it in half here, and then you just, well, you can just add those two integrals together. And that should make sense. You add the areas together. And then, if f of x is greater than 0 for all x in a to b, this means that our integral from a to b of f of x dx is going to be greater than 0. And this should make sense, obviously, right? If all the points are above the x-axis, right, then our area is going to be positive. And then if f of x is greater than g of x for all x in a to b, this means that the integral of from a to b of f of x dx is going to be greater than the integral of gx dx. And that should make sense, right? If f of x is bigger than g of x, then the area under the curve of f of x is going to be greater than the area under the curve of g of x. Now our final property, I had to draw a picture. And what it states is, if little m is less than or equal to f of x, which is less than or equal to m for all x in a to b, then the area under the curve little m is going to be less than the area under the curve of the integral, which is going to be less than the area under the curve of big M. So what is this saying, right? This should make sense. The area of big M is going to be this whole box. The area of little m is going to be this little box, right? And then we have the area under the curve, which is going to be from here to here, right? It includes the little box, but it's not going to include the whole box, so it has to be less than this. And so what we get is this property that m times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to big M times b minus a. So that is all the stuff I wanted to go over in the lecture portion of the video. Let's transition to some practice problems. Alright, now on to the practice problems. We're doing numbers 7, 17, and 19. Okay, so what is it saying? It's saying find the under and over estimates of our integral from 10 to 30 of f of x dx. And how do we do that? Well, we have to find our left-hand endpoint estimations and our right endpoint estimations. And how do we do that? Well, we know they are equal to the sum from I to 1, from I equals 1 to n, and in this case it's 5, right? Because we have 6 endpoints here, so that means we have 5 sums. And then it's times, for the left hand, times f of x to the I minus 1 times delta x. And then let's do that. Well, we need to first find our delta x. What is it? Well, we go from 10 to 14 to 18, so our delta x is 4. And now we just, okay, we do 4 times negative 12 plus negative 6 times 4 plus negative 2 times 4 plus 4 times 1 plus 3 times 4. Okay? And what is that equal to? This is equal to negative 64. You guys can do the math. I don't feel like going through, simple algebra, or addition even. And now we do the right hand. And what is it? Well, the right hand is the sum from I equals 1 to 5 of f of x I delta x times delta x. So what do we do instead? We basically take these 4 terms, right? This negative 6 times 4 plus negative 2 times 4 plus 4 times 1 plus 3 times 4. And then we just do this plus this 8 times 4. And this is going to equal 16. And we get, okay, well, our underestimation is negative 64, and our overestimation is going to be 16. And that's a huge area, or not area, but that's a huge interval. But that's okay because we were only tasked to find it with 5 rectangles when 5 rectangles is nowhere near enough to get an accurate reading. Okay, now number 17 and 19. What it says is it wants us to rewrite these as integrals, as definite integrals. So we have to do that. First, integral. Well, we look at our bounds, our interval bounds, 0 to 1. So we have the integral from 0 to 1 of, well, now this is our f of x, and then our delta x just turns into dx. So this is just e to the x over x plus 1 dx. Okay, cool. And we're done. We don't have to do anything more than that. We just have to write it out as an integral. Same thing here. Well, we have the limit as n approaches infinity from I to n of 5 times xi cubed minus 4xi delta x on the interval 2 to 7. So first we do our bounds from 2 to 7, and then it's 5x cubed minus 4x dx, and we are done, right? Because we just have to write it as a definite integral. So this is all I wanted to cover for today's video. I know this one was also long. The next video should be a lot shorter. Thank you for watching. As always, my name was Logan. Have a great day.